Okay, so this problem says a force Fx equal to minus 5x squared plus 7x acts on a particle. So this is a force, position dependent force. How much work does the force do on the particle as it moves from x equal to 2 meters to x equal to 5 meters? So if you wanted to calculate the work done by a position dependent force, that's the integral you would do. Okay. And so let's do that integral. So it's minus 5x squared plus 7x dx. So it's minus 5x cubed by 3 plus 7x squared by 2. Yep. Okay. And so when you did an integral of that, that's the function you got. So if you took the derivative of this, that would be the function you get. So this would be your U. This would be the potential energy. Okay. Now, when you take the derivative, if you had a constant, the derivative would still be the same. Okay. So, for instance, and U is defined with the negative of that would be equal to negative of minus 5/3 x cubed plus 7x squared by 2 plus c. Okay. I'm sorry? Right, because you can always add a constant. You take the derivative of that, you'll get this. Yeah. A negative of the derivative. Yep. So anyway. All right, so the work done is, and our x initial and x final are 2 and 5 meters. So 5 and 2 meters. Okay, so it's minus 5/3, 5 cubed minus 2 cubed plus 7/2, 5 squared minus 2 squared. Okay, so that's 10.5. All right, so you can calculate that work done. Okay, so the force did negative 1.121 joules of work. Okay, part B says picking a convenient reference point of the potential energy to be 0 at x equal to infinity, find the potential energy of this force. Okay, so that was the force, and you saw that this remember, the force is related to the potential energy like so. Okay. So the derivative of this is that. So negative of this function. So we want to define u. So u would be negative of that function. plus C. Okay. du by dx, negative du by dx would be d by dx of this function, d by df of this function is that. Okay. So ux is 5/3 x cubed minus 7/2 x squared minus c, but we'll call it a new c. Okay. So okay, c prime, and we'll call it a new c. All right, what is it that we want? For x equal to infinity, we want the potential energy to be 0 at x equal to infinity. Well, this is not possible because at x equal to infinity, this is blowing up, so you can't pick any constant. So actually, this potential energy function has a problem. Okay, so if you roughly plot it, okay, the x cubed part goes like that, and the x squared part goes like this. Okay. So the net function will be like that, and it'll go to infinity for the negative axis. Okay. So it's sort of an unphysical potential energy function. Okay. So it's an infinitely tall mountain to the right and infinitely deep valley to the left. All right, so there's the function plotted. Okay. So this portion is physical, this portion is unphysical. Okay, so if you had a system, it would okay, only this portion would be physical. In fact, in a physical system, this would go up, because if you leak over this hill, you would fall down forever. Okay. And that doesn't happen in real life. Okay, so for this problem, a boy throws a ball of mass 0.25 kg straight upward with an initial speed of 20 meters per second. When the ball returns to the boy, its speed is 17 meters per second. How much work does air resistance do to the ball during the flight? Okay, so if air resistance was not there, you throw a ball up, it would come back at the same speed. Okay? But because of air resistance, it's not coming as fast. Okay, and now you can understand the following. You know, in some cultures, in celebration, they'll fire guns straight up. Why are they not afraid? So remember, a bullet goes out of a gun at, let's say, 1500 meters per second at Mach 1. If there was no air drag, it would fall back at Mach 1. And it could kill you. But because of air drag, the empty shell doesn't fall as fast. Okay. So you don't get hurt. What's that?
It just still falls fast enough to hurt you. I've heard about some people
Oh, yeah?
getting, like, shot, basically.
So can it be fatal?
I don't think fatal. The person I know is it ended up shooting her knee, but I'm sure it can be fatal. Just obviously not as fast as, active shooting point blank, but.
Okay. Yeah, I don't know. I mean, it's done often enough. It seems like, at least you see in the media.
In the media.
No. I've never experienced it myself. So anyway, Boy throws a ball of mass 25 kg straight upwards with an initial speed of 20 meters per second. When the ball returns to the boy, its speed is 17 meters per second. How much work does the air resistance do? Remember, air resistance, what kind of a force is it? Conservative or a non-conservative force? I'm sorry? Non-conservative. So work done by non-conservative forces is change in mechanical energy. Okay. So here's the initial point, goes up, and there's the final point. Okay. Kinetic energy final plus potential energy final minus kinetic energy initial plus potential energy initial. Okay. Now at the initial and final location, the potential energies are the same, so they cancel each other. Or you can take them to be zero at that reference level. What kind of work does drag forces do? Positive or negative? Or zero? Negative. At the final location, it's slower. This is less than that. And the work done by the drag force is negative. Okay. So when the ball was going up, the drag force was in the opposite direction. And when the ball was going down, the drag force was. Okay, so drag and friction forces are always in a direction opposite to the motion. And theta is always 180 degrees, cosine of 180 is negative, so they always do negative work. All right, so as the ball moves in the vertical direction, its gravitational potential energy changes. And in this problem, so this problem involves gravitational potential energy. It also involves spring potential energy. Okay. So this problem says the massless spring of a spring gun has a force constant of 12 newtons per centimeter. Okay, so let's put it in appropriate units, 12 newtons per centimeter, and we'll convert that to meters. So 12 Newton centi is 10 minus 2 meters. So 1200 newtons per meter. Okay, what does this number mean? You would have to suspend a force, a weight of 1200 newtons to stretch the spring 1 meter. 1200 newtons is roughly twice my weight. Okay, so two of me would have to hang on to the spring to stretch it by a meter. This is a meter. Yeah. Right. When the gun is aimed vertically, a 15-gram projectile is shot to a height of 5 meters. Okay. How much was the spring compressed initially? So there is the uncompressed location. And so that is the distance we want to find. Now, when the object moves, there's the force of gravity acting on it, and in the initial portion of the flight, there was a spring force acting on it as well. So both spring and gravity were acting on the object. What kind of forces are these? I'm sorry? Conservative. And so the work done by these guys can be accounted for by measuring their potential energy. Okay? So these guys are good guys, so we like them. Okay? So let's say here's the initial configuration, there's the final configuration. Okay, when only conservative forces act, then mechanical energy is conserved. Okay. So we'll choose this as the reference level for gravity. So initial kinetic energy, I'll write initial and final. Initial kinetic energy plus initial spring potential energy plus initial gravitational potential energy equal to final kinetic energy plus final spring potential energy plus final gravitational potential energy. Okay. Now this energy is, any point can be initial, any point can be final along the way. So the sum of these three guys is constant through the entire motion. Okay. All right, at the initial and final point, the ball was at rest here. When it gets to the very top, it's at rest. So these two guys are 0. We've taken this to be the reference level. At the initial point, the gravitational potential energy is 0. In the final configuration, the spring is fully extended. It's in its equilibrium position. It's neither compressed or stretched. So this guy is 0. Okay, so what are we saying? You see, the spring potential energy got converted to gravitational potential energy. That's what happened. You compress this spring, it had spring potential energy, and all of that got converted to gravitational potential energy. Okay. In the middle, the spring potential energy was being converted to kinetic energy and gravitational potential energy. Okay. But in the final configuration, all that kinetic energy also got converted to gravitational potential energy. So that's what we are saying here. All right. What was the initial spring potential energy? It's 1/2 k d squared. And that is equal to mg y. Y is this distance. Okay. And that's 5 plus d. K is 1200 newtons. Mass is 0.015 kg times 9.8 meters per second square plus 5 plus d. All right, so this is a quadratic equation. Okay, so the roots of this equation are minus b, so so what we're finding is how much are we compressing the spring. D is okay. And that was in meters. Okay, so what is the solution? So you compressed it this much. Okay, 3.5 centimeters, about 1.5 inch. What do you think this means? So here's the neat thing about mathematics. So imagine the following situation. Okay, so this bullet was attached, if was sitting on that. What if it was attached to the spring? What would happen? The spring would extend and it would come to rest there. So if this was positive, the distance it would come to rest, if it was still attached, would be 3.49 centimeters above the equilibrium position. That's what that is. And you see, that makes sense. This distance is smaller than this compression. Why is that distance smaller? So for instance, if the spring was horizontal, you let go from here, it'll compress to the same location. Why didn't this guy go all the way to the top? I mean, to the same location. Because some of its gravitational potential energy increased. And so the spring potential energy had to be a little less. Okay. All right, anyway, the mathematics gives you all all the solutions. Okay, it's just a matter of interpreting them. All right, guys, we'll